To motivate personalized speech enhancement, or PSE, let's discuss this idea of generalists versus specialists. A generalist here means that the model is trained on a large set of diverse speakers and noises, hoping to universally generalize to all speech enhancement cases. Suppose our enhancement system encounters user A. They always seem to have this dog barking in the background of their phone or video calls. The universal generalist model needs to denoise user A as best as it can given its large set of trainable parameters. This would also apply to a user B, a user C, and so on and so forth. They all have different vocal characteristics and different test time environments. In order to cover all these cases, the generalist model tends to be larger, difficult to train, and more expensive to run given that they have more parameters. On the other hand, specialists are trained to solve a single task, which is a subset of the overall task. Therefore, they can be smaller, easier to train, and cheaper to run with fewer parameters. It may seem obvious that building specialized models is the way to go, but how exactly do we go about doing that? So the straightforward approach for training a speaker-specific enhancement model would be to start with the generalist model. So one could take the public dataset G and mix it up with some public noise dataset N. This model takes the mixture signal as input and predicts the clean speech, which is compared against the originating speech source. This is legitimate, fully supervised speech enhancement because the model has access to the composing signals. On its own, the generalist could be considered a zero-shot solution to PSE, since it has no knowledge of the target speaker's clean voice. Next, to make this model actually personalized, one could fine-tune the generalist model using the target speaker's clean speech data, S. Because we're relying on the clean target speaker's voice for training, this becomes a few-shot solution to PSE instead of a zero-shot solution. This strategy of transfer learning has a few issues. There's a chance that it could overfit, but more importantly, few-shot learning might not be an option. Typically, the dataset S is obtained through an enrollment procedure, where the target speaker says a few predetermined sentences in a noise-free environment. This may yield maybe 5 or 30 seconds of usable data. It's kind of a tedious process to ask users to do. Given that AI-based vocal forgery is also a legitimate concern, most users may not want to do this enrollment procedure at all in order to maximize their own privacy. Our hypothesis is that there is a dataset S tilde, which is basically the in-the-wild recordings of the target speaker accrued over test time. These are more abundant, but since they aren't obtained in a regular enrollment procedure, there's no guarantee that these are noise-free recordings. Still, since S tilde gives us some knowledge of the target speaker's voice or their noisy environment, it may be a better starting point than the big generalist dataset G. We will introduce 3 self-supervised methods to somehow make use of S tilde. Because we are working with the noisy data S tilde and not the clean data S, this is once again a zero-shot solution to PSE. And given that S tilde will be a much smaller pool of data compared to G, self-supervision may enable a more data-efficient solution to PSE. And since we only care about one speaker, the self-supervised specialist can afford to use much fewer parameters. Lastly, if we do have that enrollment data available, the self-supervised specialist can still be fine-tuned through conventional, fully supervised speech enhancement. We hypothesize that this is less likely to overfit and instead be a better performing PSE model. Now I'll explain our 3 self-supervised methods. We call our first one pseudo-enhancement. In the figure below, the blue waveform contains the pure target speaker's voice, but that is, of course, inaccessible. Instead, all we have is the noisy observations, which is the blue signal corrupted by an unknown green signal. During self-supervised pre-training, we inject the orange noise signal onto the observation, and our PSE model learns to remove the orange noise. This is our most straightforward approach to leveraging the unlabeled in-the-wild data. Our second method is essentially a regularization of pseudo-enhancement through contrastive learning. We can take the abundant noisy observations and pair up the recordings in batches. In a positive pair, we would take the same observation and inject 2 different training noises onto it. Our contrastive mixtures model will do pseudo-enhancement to both of the recordings, but it will target the same original pseudo source. With the negative pair, we can pick up 2 different noisy observations, but inject them with the same training noise. The contrastive mixtures model will once again do pseudo-enhancement for both of the recordings, but now the estimated pseudo sources should be different. The success of method 1 and method 2 are limited by how noisy those observations are to begin with. In other words, These methods will work best if the green premixture noise is sufficiently sparse. We investigate using auto-labeling to make the unlabeled data more usable. Our last proposed method involves data purification. So consider our observations, which are made up of the target speaker's voice and some unknown noises. If we were to use a previously trained signal-to-noise ratio prediction model, we can auto-label our in-the-wild data. We can map the SNR predictions, which don't have to be 100% accurate, into a cleanliness vector listed here as P. This would encourage our self-supervised PSE model to promote the contribution of cleaner frames and ignore the contribution of the noisier frames. So if we go back to our pseudo-enhancement setup, by applying data purification, it's almost as if the contaminating noises weren't there in the first place. In that regard, data purified pseudo-enhancement is a more closer approximation to true speech enhancement. Lastly, whichever self-supervised method we use, once the pre-training is finished, we can fine-tune the model using standard, fully supervised, true speech enhancement, leveraging any available enrollment data. We perform our experiment on the well-known ConfTasNet neural network for sound separation. We designate 4 different model sizes by tweaking the ConfTasNet configuration. This is done so that we can investigate the efficiency and model compression benefits. The personalization experiments are done using 20 set-aside speakers from the liver speech dataset. The exact sizes and utilization of each of these datasets is detailed in our paper. Now I'll discuss the experiment results. The pre-training methods are split up over the column sub-axes. With the zero-shot context, we look at the dark shaded bars. If the model is sufficiently large, we see that the standard unpersonalized speech enhancement model does well enough. However, when we're looking at the smaller model sizes, the generalist has less generalization power. In these cases, the self-supervised models, which are trained only using unlabeled data, achieve a better zero-shot performance. Now we'll consider the few-shot context, where we do have some clean speech enrollment data from the target speaker. The lighter bar represents 5 seconds of clean speech, while the light test bar represents 30 seconds of clean speech. We can see that for all model sizes, self-supervised pre-training allows for better adaptation when given the clean speech. In fact, the generalists do not see any improvement with only 5 seconds of few-shot data. Most notably, the performance obtained by a generalist fine-tuning over 30 seconds can be exceeded with only 5 seconds or less of the self-supervised pre-training. Lastly, if we look across the horizontal sub-axes, it's evident that self-supervised pre-training does enable a kind of lossless model compression. In conclusion, our results show that self-supervised pre-training leads to smaller, more efficient PSE models, which require less training data and still perform better. Thank you for listening.